Now we first introduce a few previous phrase mining methods. Phrase mining actually originally came from the natural language processing community called chunking or noun-phrase chunking. Okay. Essentially, so we model a phrase as a sequence of labeling problem. For example, you can explicitly label a word as the beginning of this noun phrase, then you see another word, it could be inside of noun phrases, and you may have something outside of this phrase. Okay. This will need a lot of annotation and a training effort. For example, you may ask domain experts to annotate hundreds of documents as training data. Then we can use the software, use the methods to train a supervised model based on part-of-speech features, like part-of-speech tagging. Okay. The recent trend is also try to use web n-grams. Those web n-grams, we can get some statistics. We'll be able to use distributional features to generate good phrases. This one was done by Bergsman and others in 2010. The state-of-art performance using this approach is about 95% accuracy and about 88% of phrase-level F-score. However, this method suffers from the high annotation cost, and then it will not be scalable to a new language. For example, you label English, it may not be used for French. Or a new domain, like you label the news, may not be able to be used for computer science or new genre. Okay. So it may not fit domain-specific dynamic emerging applications. For example, there are lots of new articles in scientific domain, in computer science domain, or like medical domains. Or the machine may generate a lot of query logs. Or social media may contain Yelp and tweet data. This kind of data set is so domain-specific and dynamic, so it's hard to assign or train every subset of such data using annotation. So people want to develop unsupervised phrase mining methods. Actually, many unsupervised phrase mining studies are closely linked with topic modeling. Okay. Topic modeling essentially is a new recent developed method, represent topics by many phrase words. You get every topic is represented by a word distribution, and documents, a set of documents actually may contain many topics in different proportions. This method does not require any prior annotations or labeling of the documents. It relies on statistic topic modeling algorithm. One of the most popular ones are LDA, or we call latent leash allocation, developed by David Bly and others in 2003. Actually, to do phrase mining using topic modeling, there are three different methods. One is we simultaneously infer the topics and the tokens, the phrases, at the same time using some kind of generative model. Okay. The second method is first using generative model to generate topic models, and using topic model try to group different words into n-grams, into phrases to visualize such topics. The third one, the newest developed one, is first doing phrase mining before we do topic modeling. That means we mine phrases and impose such phrases on the bag of words modeling process. So let's look at the first method. We call strategy 1, is simultaneously inferring phrases and topics. There are studies, the first one in 2006 was called a bigram topic model. That means we use some kind of probabilistic generative model to look at the previous words and the topic to see whether the next word should belong to the same topic, should be a phrase. And its generalization from this bigram topic model is TNG, or called topic n-gram modeling. It was developed in 2007. It is a probabilistic model, generate words in textual order, then create n-grams by concatenating successive bigrams. Then the third study is that by Lindsay and others in 2012, called PD-LDA, or phrase discovering LDA. For this method, we first view each sentence as a time series of words. Then using PD-LDA and assume the generative parameter, like those topics, may change periodically. Then each word is drawn based on the previous M words, based on the previous context, and the current phrase topic, so we can generate whether this word should be there or not. Okay. This method, due to its high model complexity, okay, it tends to overfitting. That means it overfitting to a particular topic. Sometimes it may not generate very good quality phrases. Another one it has high inference cost because of this complete generative process. It runs pretty slow. The second strategy is post-topic modeling phrase construction. That means we first do topic modeling, then we do phrase construction. The first such work called TurboTopics. TurboTopics was developed in 2009 by David Bly and John Lafferty. The general idea is first do latent deletion allocation to do topic modeling. Then, based on topic modeling, we do post-processing to construct the phrases. Okay. That means we first perform LDA on corpus to assign each token a topic model. This is topic modeling. Then we will merge adjacent unigrams with the same topic model by distribution-free permutation test on arbitrary length backoff model. For example, you can see this. If you see phase transition and you see phase transition are in same topic number 11, and they are consecutive, likely they could form a phrase. You can recursively merging and generating such phrases. We will end recursive merging when all significant adjacent unigrams have been merged. So then you will be able to generate some good phrases. Another method called CURT is also first do topic modeling, then do phrase construction. It was developed by Marina Danilevsky and others in 2014. It take first do some LDA and then do post-processing for phrase construction. Okay. The first one the same as TurboTopics. Then the interesting thing is it performs frequent pattern mining to extract candidate phrases with each topic, then perform phrase ranking based on the 4 different criteria. One criteria called popularity. For example, if you see information retrieval is more popular than cross-language information retrieval, then information retrieval as a phrase will rank higher than the cross-language information retrieval. The second criteria is concordance. For example, if you see strong T quite often rather than you see powerful T, or you see active learning quite often rather than you see learning and classification getting together as a sequence, then we will say strong T and active learning has higher concordance. The third one, called informativeness, essentially is whether the phrase generated is more informative, contains richer information, discriminative. For example, if you see this paper, it's almost every research paper, they have a lot on this paper. So this paper is more like a stop word. Here it's more like a stop phrase. It is not informative. It's ranked low, likely should be removed. The fourth criteria is completeness. For example, you see vector machine. Almost every time you see this phrase, you also see support vector machine. That means vector machine may not be complete, and support vector machine is a complete phrase. Okay. Then not only you can compare phrase quality with the same length, in many cases you can compare phrase quality of mixed lengths. That means you compare vector machine versus support vector machine. Rather than you think they are the same lengths, you compare them. With this process, frequent pattern mining plus phrase ranking, this method generates better quality phrases.